Hello everyone, and welcome to our last chapter of this course, our pre-calculus course. We're in chapter 12, and in chapter 12 we're going to look at some miscellaneous topics. Now they do seem to be unrelated, some of them. So for example, mathematical induction and geometric series, or the binomial theorem, geometric sequence series, and mathematical induction. So they seem to be unrelated, and for most parts they are the ones that I mentioned, but there are also some overlaps of concepts amongst them. But whatever that might be, we're looking at 5 sections in chapter 12, and these sections are rather brief, and we'll see how that turns out. We're going to begin with section 12.1. Now the entire listing of the topics that I have, these are extremely important in your calculus series courses, especially the sequences and series. You learn about those in second semester or third quarter calculus courses, and they are very applied and very fascinating. The idea of mathematical induction, it's a way of proving statements involving natural numbers, sequences of natural numbers. So mathematical induction directly relates to section 12.1 as well. And of course, the all-important binomial theorem, which is used extensively in the area of probability theory. And of course, it has other usages as well. So let's begin with section 12.1. In section 12.1, sequences and series. So to begin with, let's define what a sequence is. Very simple. A sequence is a function, just like your other functions that we worked with throughout the course, except the only difference is the domain of the function. So if the domain is a set of natural numbers, and remember your natural numbers are pretty much your counting numbers, 1, 2, 3, 4, dot, dot, dot. So if that is a domain of the function, then it produces a sequence, what we call a sequence. Now the range, of course, depends on the formula for the sequence. So the range is all real numbers, just like before. Now to give you an example, for instance, when we talked about f of x, x squared, remember we talked about the parabolas. And if I just focus my attention to values that are greater than or equal to 0, then my parabola is going to look something like this. Now this function is continuous, right? Because there are no holes, gaps, jumps, or asymptotes in the graph of the function. So we have nice continuity of the parabola. And that is a function. Now we can turn this into a sequence by, first of all, using, instead of x, I'm going to use n to differentiate between the variable here. And instead of x, again, I'm using n. And by the virtue of defining the sequence, its domain, the set of natural numbers, I don't need to repeat that one. But if you actually look at the set of natural numbers, and if we plot these points now, n for the variable, not x, and up here we have the function value. So I'm going to start with like 1, 2, 3, and so on and so forth. So you get 1 squared is 1, 2 squared is 4, 3 squared is 9, like that. Therefore you have the general trend is like a parabola, except notice you have discontinuities, right? You only have outputs, values at very specific points. You don't have the continuity any longer. Okay, and that is very important in higher mathematics, the fact that we do not have continuity in the function. But there you go. This would be an example of a sequence. So I can write this f of n using the notation I have, or in some textbooks they use curly braces and then a sub n, and some just write it as a sub n. So those are the ways to write this. And finally, you can actually even write it like this. You simply put the function, the formula for the function, in curly braces. So those all mean the same thing. Okay, there are different representation of a function whose domain is the set of natural numbers, in other words, a sequence. Now let's stay with the example that I have. So suppose for different values of n now, remember n is only allowed to be a set of natural numbers. And then here's n squared, so I get 1, 4, 9, 16, and so on. Now the fact that the set of natural numbers is an infinite set implies that all sequences are infinite sequences. So if I just write the sequence of numbers now, not the natural numbers, but the actual outputs, the n squares, that sequence is going to look something like this. 1, 4, 9, 16, and so on, right? So this is what the sequence is. And the sequence is going to be what we call an infinite sequence. Okay, so this is going to be an infinite sequence. Because again, the set of natural numbers is an infinite set. Now, if we only look at a finite number of elements in the sequence, then the sequence becomes finite. So for instance, if I just look at 1, 4, 9, 16, 25 and stop there, if for some reason I just need the first 5 terms. So for that one, then the sequence becomes a finite sequence. Okay. Now each of these numbers, the 1, the what you call it, the 4, 1, 4, 9, and so forth, all the way. These are called the terms of a sequence. So each one is a single term of a sequence. So we got many terms in this sequence, right? The terms of the sequence. The terms of the sequence are the outputs from the function. Okay. Now sometimes we can write sequences like this. So I have 1, 4, 9, 16, dot, dot, dot. And at some point, I just simply put, notice the formula for the sequence, which is n squared, and I pick up dot, dot, dot to the right of it. So that's another representation of a sequence. Now, the terms of a sequence, the first term is going to be a subscript 1, the second one, a subscript 2, the third, a subscript 3, and so on. The one that represents the formula for the sequence, we call that the nth term, the nth term. Okay, and the nth term is just the general formula for the sequence. So my nth term, there you go, is the actual function that generates the sequence of outputs. All right, so that would be again the nth term. The nth term is also called the general term. Okay, so we have that as well. Let's take a look at another example. So this one, I'm just making something up here. This is interesting. Let's take a look at -1 to the n. So here's my sequence. I can put it in curly braces like that. Okay, so let's actually write out the first few terms of this one, shall we? Remember, n is a set of natural numbers. So n is naturally, no pun intended, so n is naturally going to be counting numbers, 1, 2, 3, and so forth. So let me just, let's start with this. I'm going to have -1. Well, let me tell you what I'm doing in a moment. Let me just put a few more here. I'm going to put the first 5 terms and so on. Okay, so when n is 1, that's -1 to the first power, then n is 2, then n is 3, n is 4, n is 5, and so on, right? Okay, let's see what happens to these terms. -1 to first power is itself. -1 squared is 1. -1 cubed, -1, -1 to the fourth one, -1 to the fifth, and so on. So this is interesting. It looks like I'm looking at a sequence of ones and -1s, right? A sequence like this, we call it an alternating sequence. It's alternating because the terms alternate between plus and minuses. Okay, so keep in mind, anytime we have a sequence that alternates, we know, drawing from this example, we know that there's going to be -1 to the n in there somehow. Now suppose I have -1 to n plus 1, where the sequence now looks like this. Remember, we start with n equal 1. So when n is 1, I have 1 plus 1, that is 2. Next term, 1 plus 2, that's 3. Next one, 1 plus 3, that's 4. And you can kind of see the pattern that this generates. Negative 1 squared is 1, negative 1 cubed, negative 1, negative 1 to the 4th, negative 1 to the 5th, and so on. Now, if you look at this sequence and look at the one above it, they're also alternating, right? In fact, they're both alternating. The difference is whether you start with a positive or negative 1. Okay, you see that one? So if my sequence begins with a negative, and that's when alternating begins, negative 1, 1, negative 1, and so on, then I go with negative 1 to the n. But if the alteration in sign starts with a positive 1 and then goes through cycle of plus, minus, plus, plus, minus, plus, minus like that, then I know that it has to be negative 1 to the n plus 1. Again, this is very important, folks, because a lot of times we get sequences that are alternating. Okay, so let's take a look at another example here of a sequence. So this time I'm going to call sequence B sub n. The letter doesn't matter. It could be A, B, C, D, whatever. And this one I'm going to go 3 to the n divided by 2 to the n plus 3. So suppose this is my sequence. And we just want to write the first, let's say, I don't know, 4 or 5 terms, or whatever. Remember, n starts with 1, right? So I'm just going to write this for now. I'm just going to write 5 terms. I'll put the exponents in color in just a moment. This just helps it go a little faster. And 3 over 2 plus 3, that's 4 terms. Let's go one more term, and that will be 5 terms. Now let's complete it. Now n starts with 1, so I'm going to go 1 on top, 1 on the bottom. 3 squared, 2 squared. 3 cubed, 2 cubed. 3 to the 4th, 2 to the 4th, 3 to the 5th, 2 to the 5th. You see that? This other 3 is constant. It doesn't involve n, so it's not going to change. It's always going to be a fixed number. And that's it. That's listing out the terms of a sequence. And of course, we always evaluate them, correct? So let's evaluate this one. And when we evaluate it, we're going to get 3 over 5. Next one is going to be 9 over 7. Next one is going to be 27 over 8, and 3 makes 11. 3 to the 4th, 81, and that's 16, and 3, 19. 3 to the 5th, that would be, what, 243? Because that's 81 by 3. 2 to the 5th is 32, and 3 makes 35. And there you have it. We have the first 5 terms. So this is A sub 1, A sub 2, A sub 3, sub 4, and sub 5. And there we have the list of them. Okay, let's take a look at an alternating sequence now. I'm going to call this C sub n, and the formula for C sub n, I'll make it easy. Let's go negative 1 to the n, and we're going to just go n plus 1 times n plus 2. How's that? And by the way, it's a lot easier. It's a lot easier to, once you're given the functional form of the sequence, to write out the terms, because you pretty much have the formula. You plug in the input, 1, 2, 3, 4, and so on, and you get the outputs. The other way around, once they give you the outputs requiring the formula, that's going to be a heck of a lot harder. So, for example, imagine you were given the sequence of numbers like that, and they ask you, what's the formula? What's the function that generates the sequence? That would be a lot more challenging, wouldn't it? And we will do that in a moment, but for some that are not, the examples we do are not going to be too complicated, just to get the point across here. Okay, let's write out the first few terms of this sequence. Remember, n starts with 1. Again, in the just because I see this as a pattern, I'm just going to go negative 1. I'm going to leave n blank. The spot where n is, I'm going to leave it blank because I'm going to use different colors for that. And there you go. So I'm just going to go +1, +2. And doing this also, I'm hoping that I'm emphasizing the pattern. See, I'm writing this without even thinking about the formula, any values, anything specific. Because we're interested in the pattern that this sequence generates. Okay. And here's +1, and then blank +2. Let's write the first 4 terms. Now I'm just going to actually put in the numbers. We start with n1. So everywhere you see an n, I see it in 3 places, right? 1, 2, 3. In those 3 places, we're just going to replace n with the natural number. Next time it's going to be 2, 2, 2. Then it's going to be 3, 3, 3. It's going to go 4, 4, 4, like that. And then we actually evaluate the fraction. So there you go. That is the sequence. Now in the numerator, remember we have -1 to the end. That's going to cause these terms to alternate. So -1 to the first, that's -1. Denominator, 1 + 1 is 2. 2 times 3 is 6. -1/6. Next one, -1 squared is 1. The denominator, 3/4. That is 12. Correct? What is c sub 3? The third term, -1 cubed is -1. 4 times 5, 20. And the last one is going to be 1. 5 times 6, 30. See how that goes? So we have again the sequence that alternates between negative, positive, negative, positive, and so on. Okay, and the next thing we are interested in this section is the idea of factorials. Let's talk about factorials. Now, factorials play a tremendously important role in mathematics. They appear in so many places. It's just unbelievable. But let's see, what is a factorial? A factorial, well, the notation for the factorial is the exclamation symbol. So this is just the factorial notation, like that. Now, when I write it quickly, it's going to look like this, right? I'm not going to take time to make it look nice and fancy like that. So that's what it's going to look like. So what is this factorial? Well, we can write factorials for every positive integer number or every natural number. We can write a factorial for. Of course, we can do it for other numbers too. It's just, again, for what we're doing, we're dealing primarily with positive integers, so that's what my focus is on. So here's 3 exclamation or 3 factorial as we read it. Now, what is 3 factorial? Well, the word factor means product of 2 or more things, right? So for example, 2, 3, 4. These are factors, right? Which multiply 2, 24. So they become factors of 24. So the word factor in factorial suggests we're doing some kind of a multiplication, and indeed we are. Now the difference is you always just start with the number that you want to find the factorial for, and then you go all the way down to 1. So it's every natural number starting from the number that you want to find the factorial for all the way down to 1. And of course you multiply and get the answer. So if I want, for instance, 5 factorial, again, that's going to be 5 by 4 by 3 by 2 by 1. It's always descending natural numbers all the way to 1. It has to go to 1. And this one turns out to be what? 20 times 620. Notice, by the way, factorial is a function and it grows very rapidly. So each time, because each time you multiply by a larger number as you go from 5 to 6 to 7, right? So you're multiplying, and that multiplicative effect takes hold of the function and it makes it grow very rapidly. Now 0 factorial, by the way, is 1 by definition. Okay, so it's not 0. In fact, 0 factorial is the same as 1 factorial for our work. They equate the same number. They both equal 1. Now we can write this factorial in more general form, n factorial, where n is a natural number here. Is going to be product, remember, of the number, and then we go one less than that one less each time you go one less than the previous one, as you can see here, all the way down to 1. So the last product's going to be 3, 2, 1, like that. Okay, and that's what n factorial is. There is an efficient way of writing it, and it's not usually in pre-calculus textbooks, but it's not difficult, so might as well show it to you. If you use pi here, and remember here pi 3.14, don't think about that. Okay, they just call a pi product. They use pi, so it has nothing to do with 3.14. So this is the pi product of from 1 to n of I. So here's how the pi product works. It starts with 1, then times. Next time I is 2, times, next time 3, times, all the way up to n. So that is what we call a pi product. Okay. And there you have it. Now, let's talk about a recursive definition. Okay, this is another way. So if you're given a function, if you're given a sequence like this, then we can easily write it, right? We call this the functional form. This is the functional form because you have a formula, a function. Okay. Now, we also have what we call the recursive definition. So let's talk about the recursive definition here of a sequence. This recursive definition is the second way of defining a sequence. Now, what is a recursive definition? In a recursive definition, the nth term, a sub n called it, is defined in terms of previous terms, the terms preceding it, of the term or terms preceding it. And that's what that is. And then the rule or the formula, it's called the recursive formula. Okay, so let's see how this is going to work. My example. So let's say I'm going to define my first term to be a number, a random number, 4. And here's my recursive definition, the nth term defined in terms of the previous term. So it's going to be 3 times the previous term. You see that? That's what the recursion is. Now, recursions are big in computer sciences. A lot of things are written, a lot of the program fragments are written using recursions. So if you're a computer science major, you're going to work with recursions extensively. But the basic idea is the same. The computer scientists call a sub 1 equal 4 a stopping case. Stopping case, just to put that out there for the computer scientists. Okay, so for us, it's just the first term. Now let's see how this works. Suppose I want to find the second term. The second term is 3 times 2 minus 1 is 1, 3 times a sub 1, which is the previous term. Well, the previous term, the first term, is 4, right? That's my initial value. So that's going to be 12. I'm going to write the sequence here. So the sequence is going 4. Next one is 12. And let's see, what is a sub 3 going to look like? The third term, it's 3 times the one before. This is going to be 3 times the one before is 12. That's 36. And the next one, I guess you multiply this by 3 and you get the next one, right? So the next one would be 108, the next one 324, and so on. You see how that works? It's very important to have that stopping case or the initial case. Otherwise, we will not be able to write the sequence. Now, although I have the sequence of elements here, right? These are the outputs. But the question might be, what is the function, right? What is the function that's capable of generating this? In other words, what is f of n? So we're going to that goal. We're trying to find the function. So with recursions, although we can generate the terms of a sequence, the recursion doesn't give us the functional form. Keep that in mind. it's capable of generating terms as we want them, but it never gives us the functional form, which is, for most of our work, that's what we are interested in. Okay, so that's what the recursion is. Now, if I want to know what is the functional form of this, at this point, I can just kind of guess, right? I can guess, for example, I can say, well, when n is 1, it's that. When n is 2, when n is 3, when n is 4, when n is 5. So can I say f of n is whatever? Let's see, well, what's capable of generating the sequences when n is 1, 2, 3, 4, 5. So let's do it for this one actually. Let's see if we can find a functional form. Now remember, it's all about the pattern at this point because I just made that up. So it's not any special kind of series, let's say. So the pattern I see is this. So I start with number 4. 12, that's 4 times 3. 36, that would be 4 by 9. 108 is 4 times 27. 324 is 4 times 81. So I see that there's going to be a 4 in this function. Now think about 3 here. 3 to the first is 3. 9 would be 3 squared. 27 is 3 cubed. 81 is 3 to the first. 3 to the fourth. And the first term, 4, I can think of it as 4 times 1, which would be 3 to 0, right? So in each term, I have some power of 3. So I'm going to go 3, 2, because I need to get 0 when n is 1. I'm going to go n minus 1. Let's see if this works. When n is 1, I have 3 to 1 minus 1, which is 3 to 0. That's 1. When n is 2, 3 to 2 minus 1 is 3. And yes, it's going to work. So you see how I created this? I'm simply looking at the pattern. Therefore, this is now the functional form. And this works when n is 1, 2, a set of natural numbers, right? You see the difference between the recursive definition and the functional form. So both of those are ways to express sequences. Okay, let's do another example here. For this example, let's say I have the sequence that alternates -2, -4, I'm going to go 6, -8, 10, and so on. So clearly I'm thinking a sequence of even numbers, right? And of course the sequence alternates, right? It goes plus, minus, plus, minus, plus. Now we already did an example for alternating sequence, right? Plus, minus, plus, minus, plus, and it was up here, wasn't it? And there you go, plus, minus, plus, minus, plus. So I'm just going to borrow from that. I know I'm going to have -1 to the n plus 1 in this functional form. So I'm going to say that for this one, and you can write it as f of n or curly braces. So let me just say that f of n is going to be -1 to the n plus 1. That takes care of the signs. You see that? So I'm thinking when I look at the sequence as a sequence of just signs, plus minuses, this will pick up the sign. And then I'm actually going to now focus on 2, 4, 6, 8, 10, all as positive terms, right? Now remember, when n is 1, you get 2. When n is 2, you get 4. When n is 3, you get 6. And 4, you get 8. So, and 5, you get 10. So I guess if I multiply each of those by 2, then I get the sequence of even numbers. And there you have it. That'll be the formula for this sequence of alternating even numbers that start at 2. Okay. Now let's talk about series. A series, anytime we add the terms of a sequence, the result is called a series. So a series is simply sum of the terms of a sequence. That's all that is. So if you add, for example, the first in here, if I add the first 2 terms, I get -2. Add the first 3 terms, I get 4, and so on. Each of those will be a series for us. Okay. So what does the general form look like? A sub 1, if I add a sub 2, if I add a sub 3, and again, depending on how many terms I want to add. If I go all the way to the nth term, then this would be the sum of the first n terms. Right? Now, if the series, remember, all series by nature are infinite, right? So this is going to be a finite series because I'm counting up to n. But if I let the sum go beyond the nth term all the way to infinity, look at this one, dot, dot, dot. See, it keeps on going. Then this is going to be an infinite series. Now, for some category, some group of series, it is possible to find the sum to infinity, even though there are infinite number of terms. I mean, you find them in a limiting sense. And for others, we cannot. So for example, if I have a series 5 plus 10 plus 15 plus 20 plus, the pattern goes on forever. This sum is going to get too big, right? It doesn't come to a point. So this sum is going to be infinite. This is an infinite sum. And in technical jargon, they call it they say the sum diverges. Okay, that would be the appropriate way to say that. We say the sum diverges. Whereas if I could write a single number for it, we say the sum converges. Now, having talked about series here, what a series is, let's introduce the summation notation. Okay, so let's talk about sigma or summation notation. So, what is a summation notation? This is Greek sigma. There are two sigmas in Greek alphabet. One is this one, the one on the left, the one, and then the one to the right. The one on the left would be like capital S for us. The one on the right is like lowercase s in Greek alphabet. Now the sigma on the left, the sigma on the right, by the way, they use this in statistics a lot. But not just the statistics, they use it in physics and sciences as well. I'm just saying that if you take statistics, you will see this again. And usually this sigma represents like the population standard deviation. Now in physics, it could mean something else. It could be shear stress in engineering, whatever. The one we are focusing on is capital sigma. The sigma is what we call a mathematical operator. And the sigma is simply a command to add. That's what that is. The capital sigma. This is the one we're dealing with, not this one. Okay? So that's a command to add. Now, what do I mean by a command to add? So suppose I have sigma here, and every sigma has what we call an index. The index is a dummy letter. It could be A, B, C, D, E, F, G, whatever. So K is very common. It's the one that's used in a lot of textbooks. So I'm going to say it's usually I, K, or J. So I'm just going to say with K this time. Okay, K is called the index of summation. And the index can start from really any integer, but typically it starts from 1 because we're talking about sequence whose domain is a set of natural numbers. So it makes sense to start with 1, but don't be surprised if K starts with 0 sometimes. Sometimes it may even start with a negative integer like -1, -2. So please be flexible, but for most parts, K is 1. And then it goes to N. Now, K is the index. 1 is called the lower limit of summation, and N is called the upper limit. And these are natural numbers, counting numbers. So it starts from 1, then it goes 2, 3, 4, 5, all the way up to N. And usually in front of sigma, you have some kind of a formula. But for now, I'm going to keep it simple. I'm just going to go A with a subscript k the same as the index. So how does this work then? So here's how it works. You start with A. The subscript starts with 1, right? And there you go. K starts with 1. So you plug in a 1 here for the subscript. And then because the sigma is a command to add, here's where the commands to add. Next, I'm going to add y because I see the presence of sigma. It's a command to add. So I'm going to add. Next time around, we're going to increment k from 1 to 2. We increment by 1 and only by 1. Everyone who uses sigma notation in the world, in every field of endeavor, will increment the index by 1, never by 2, never by a half. Always increment by 1. The starting point may be different, the upper limit may be different, but the increments has to be in 1 unit increments. So we're going to increment it to 2 and then add. Why are we adding? Because of sigma. Next one is going to be A. This time we increment to 3 and then add. You keep doing this. So you count. See, I'm counting 4. And you increment and you add. Right? Now, how far is this going to go? 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. Well, it's going to go as high as the upper limit, in this case, n. So that's where it stops. It counts n and it stops. And there is the expanded form of that sigma or summation notation. Okay. Now, in general, when you see sigma dot dot dot, that means the sum of whatever is in front of it. This is the sum of whatever is in front of it. Okay, so in the case I have my example, sigma a sub k, that means sum of a sub k's. That's what that is. Okay. Now, let me do a quick example of, let's say we want to write the sigma. Okay, we want to just expand the sum. Suppose my sigma is, I'm going to go k squared over 2, and then I'm going to go k from 1 to 3. So this is going to go 1 squared over 2 plus 2 squared over 2 plus 3 squared over 2, and we stop. So the sum goes, as we say, from 1 to 3. And then you actually evaluate the fraction, a half plus 2 plus 9 halves, right? And that's going to be 12. There you have it. That worked out nicely. So that's how you expand the sum. What if the sum went from k1 to n of k squared over 2? Now this time I'm doing the same thing. 1 squared over 2, 2 squared over 2, plus 3 squared over 2, except, notice, keeps going until I reach the upper limit n. So it's going to be n squared over 2, and we can leave it like that because I'm not going to be able to get a number out of this one. Okay. Now, let's actually express a given sum using sigma notation. So how is this going to work? In other words, suppose I have a half, 2/3, 3/4. So you can see the numerator go 1, 2, 3, 4, 5 like that. The denominator is 1 more than the numerator. So just 1 more in anticipation. You can see you would expect me to write 5, 6, and I did. And suppose this is going to go all the way to, I'm going to go to 13 on top and 1 more, 13 plus 1 on the bottom. I could have written 14, couldn't I? But I just want to show you the pattern. Okay, so how would the sigma notation look for this? Here's my sigma. Now, as far as writing sigma goes, and you will see I have formulas for sigma coming up. Textbooks kind of write it like this. I tend to write it like this. Sometimes people write it like this. So it depends on the mood. It depends on how fast you write it. So all of these are variations with me, and I think they're all acceptable because no one's complained so far. Now, one thing that's not acceptable and it will raise eyebrows is this. And that's not sigma. Okay, so please do not write it like that. That doesn't resemble anything even close. I mean, I can go like this even, and that's a stretch, right? That's kind of crazy sigma, but that's much better than your italicized E. Okay, or the, not yours, but the italicized E that some people write it. I've seen that happen a lot. So when I usually see it, I'll try to correct it. Okay, how are we going to write this? Remember, in front of sigma, there's going to be a formula. Now, we need to handle the index k. Well, depending on if you start with the top or the bottom, I'm looking at numbers 1, 2, 3, 4 like that. So I'm going to say k starts with 1, goes all the way to 13. So upper limit is 13. Now, what do you think is going to look on the fraction? What's going to be the fraction? The numerator, 1, 2, 3, 4, 5. What's changing, by the way, in the fraction or the expression? What's changing from term to term? That's going to be replaced by k. Okay. So what's changing in the numerator are the numbers 1, 2, 3, 4, 5. So I'm just going to represent that with a k, not replace, but represent it using k. Now in the denominator, if you see 2, 1 more, 1 more, 1 more, 1 more. So every one of those, 1 more. So if my numerator is k, denominator is 1 more than that. And there you go. We express that sum using sigma notation. Let's try another one. Suppose I have 1 minus 1/3 plus 1/9, negative 1/27, and so on. And let me actually write the pattern for this one. Let me go negative 1 to the 6th. Remember, that's what's causing the alternation. And the denominator is going to be 3 to a power. I'm going to go 3 to the 6th power. Okay, so how are we going to write the sigma notation for this one? Again, I see I have 3 to the 1st, 3 squared, 3 cubed, and this is 3 to 0. I can say 1 is 1 over 3 to 0. So I have powers of 3, correct? So for this one, I'm going to say my k actually starts from 0 and goes all the way up to 6. Then I'm going to have negative 1 to the k, right? And that starts with a positive sign times 1 over 3 to the k. Looking at the pattern is all I did. And there you have it. Now, if you wanted k to start with 1, then we may have to do some adjustment, right? So how is that going to work? Well, if I want k to start with 1, remember, so here I have to have 3 to 0. This doesn't change. 3 squared, 3 cubed, and so on. So if I want k starts with 1, so that means when k is 1, I have to get 0 here, right? So I can go k1 and then go negative 1 to k minus 1 or plus 1 here. I'm going to go 1 over 3 to k minus 1. So now if k starts with 1, the first term is going to be 1 minus 1, 0, 3. When k is 2, 2 minus 1. See, I'm getting the same pattern in the denominator. And instead of going all the way to 6 now, because this is 1, 2, 3, 4, this becomes now the 7th term. So I'm going to go all the way to 7. And you can see that it works. 3 to 7 minus 1 is 3 to the 6, and that's the denominator. Now, just to make sure I got the sign correct, when k is 1, negative 1 to 1 minus 1 is negative 1 to 0, which is 1 positive. Next one will be negative, positive, negative. I'm good with this. So there you go. You could have, by the way, negative 1 to k minus 1 would equal to negative 1 to k plus 1. So you can, if you like to, you can go to negative 1 to k plus 1. And you can try this, you see that it works. Okay. Alrighty. And there you have that one. Now, let's do one more example, and then we'll put the finishing touches on the next topic in this section. So let's say this time I have, I'm going to go 2/3, and then I'm going to go negative 4/9 plus, let's make this 827 minus so on. So hopefully again you'll see a pattern in this. And notice dot 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 means this is an infinite, right? This is an infinite series. So let's write the sigma notation for this. Well, the sigma notation is going to be, I'm going to go from 1. The upper limit, by the way, for infinite, we put infinity symbol. And remember, the sign starts positive, then negative, and so on. So I'm going to go -1 to k minus 1, just like the one above it. That gives me the sequence of plus minuses that I need. Correct? Now, for the fraction, and I'm sure everybody here picked this up, you can think of 2 as 2 to the first, 4 would be 2 squared, 8 would be 2 cubed, and same thing in the denominator. So it looks like these are powers of 2 and 3, same powers in fact. 2 to the first, 3 to the first, 2 squared, 3 squared, 2 cubed, 3 cubed. Well, I can write it as 2/3, right? And write it to the kth power. 2/3 to the kth power. And there we have that one. We're able to write it in a more concise form, the summation notation form. Now, there are some properties of sigmas that we're going to look at, and some special series have actually a closed form where we can find the sum of the series. So that's what I'm going to do. I'm just going to copy these formulas now for you, and then we'll talk about them. And here we are. So we have these 8 column formulas in this section that we're going to go over. The first few, the first theorem, summation notation properties. These are just properties of sigmas, which there's 4 of them. The latter 4 are formulas to find the sum, actually. Okay, these are not properties. These are actually give you the sum. So let's start with the first one, numbers 1 through 8. The first one, so to start with, suppose we have 2 sequences, A sub n, B sub n, and C here is a constant, okay, is a real number, could be whatever. So if you have the sum of C times A sub k, you can actually bring, look at the end result here, you can bring the constant outside of the summation. And here's the justification for it, why. So remember, a constant multiple of a sequence, you can bring the constant in front of the sequence. I'm sorry, series. Same thing with the sequence. But we're dealing with series here. If you have the sum or difference, number 2 and 3, sum or difference of 2 series, get sum difference. So the sigma of sum and difference would equal to sum difference of sigmas. That's what these 2 properties are. The last one, actually, what is the last one telling us? The last one will enable us to calculate or write the series. Notice k, the lower limit starts with j plus 1 to n. This is the series is the same as the series that it starts with k equal 1, right? K equal 1 all the way to the end, and then you subtract from 1 up to j from it. Well, if let's say, for example, I have a series that has 100 terms from 1 to 100, and I only want the last 10. Okay, so I'm going to go 1 to 100 minus 1 to 90 or 89. Well, let's see, the last 10. 1, 2, 3, 4, 5, 6. Yeah, up to 90. So I'm going to go from 1 to 100 of the series and subtract 1 to 90 from it, and I get 1 from 91 to 100. I mean, not 1, but I'll get a series, the one that is from 91st term to 100. So this will allow us to actually combine series the way you see it and find maybe the sum of terms in the middle of the series or the latter part of the series. They don't necessarily have to start from the first position. Now, number 5, if you have, if you're adding or summing a constant, so for example, suppose I want to do k from 1 to 5 of 10. Well, how does this work? Because now my index is k, but 10, there is no index in 10. What's in front of sigma? So how is this going to work? Well, when k is 1, the number is 10 plus k2, 10. See, that number is independent of k. So each time I'm going to count it until I eventually reach the top number, right? 5. So I go k1, 2, 3, 4, 5. So that means 10 added with itself 5 times, which is a repeated multiplication of 5 by 10. So that number n goes here times 10 is what's in front of sigma, and that's what this tells us. So the sum of a constant, from 1 to n, you multiply n times the constant. Formula number 6, this one says that the sigma of k, which means 1 plus 2 plus 3 plus all the way up to n, is equal to n plus 1 over 2. Now there are different ways you can prove this one. There's geometric way actually you can show these, all three of these, number 6, 7, 8. But for instance, let's say if I want to prove this one, a simple proof is this. Well, sigma k, as you see, is 1 plus 2 plus 3 plus n, right? So call that s sub n, which we call it the nth partial sum. That's what we call that, nth partial sum. Partial, because remember the series are infinite. We're looking at portion of that infinite sum, so we call it partial sum. Now, if I write the same series going the other way around, n, let me actually do this. So I'm going to go before the nth term is n minus 1, then you get to the nth term, call that the nth partial sum. Now, if I write the series, I wrote it from left to right. Let's write the same series, this time from right to left. So I'm going to go n plus n minus 1. Next one would have been n minus 2 plus 2 plus 1, correct? All right, same series written backwards. So it's going to be the same sum, isn't it? And then let's add these two series together. On the left, we're going to add in columns, so I get n plus 1 plus these two add to n plus 1 plus these two terms add to n plus 1. Isn't that cool? And plus the last two terms, n plus 1 plus n plus 1. And when you add s sub n by itself, we get 2s sub n, right? Like terms. Now, how many n plus 1s are there? Well, there are n terms, right? N terms. So I can write it as n repeated addition. That's definition of multiplication. So that's n of n plus 1s that equal to 2s sub n, correct? And there it is, 2s sub n. Now I can solve for s sub n, divide both sides by 2. I get n plus 1 divided by 2. And there we go. That is the formula that you see up here. That's one way to do it. Now these other ways, usually when we do this, like in calculus classes, I use a method of telescoping sums to show these formulas. And also they're shown by induction. You can prove these by induction, but the induction actually doesn't give you the details on how the right side came about. The induction. We'll talk about proof by induction in section 4. Okay, and let's see, we're almost done. Let's just take a look at a few examples of using these the formulas that you see here. Okay, these formulas. So for example, suppose I want to find the sum from 1 to, let's go 20 of, I'm going to make 5k plus 3, something like that. So using properties of sigma, I can bring a constant outside of the summation. k1 to 20. And then sigma of the sum is sum of sigmas. So that's going to be sum of 2 sigmas of 3. So what did I do? I used two properties here. Let me show you which ones. I used this one when I split it into two sums, and I used this one when I brought the 5 outside, right? I used the first two properties of summation. Now, to find the sum, I'm actually going to use number 6. Okay. Number 6. The sum is going to be n plus 1 divided by 2. That's using the formula. Plus, to find the sum of 3 from 1 to 20, I'm going to use formula number 5. I'm just going to multiply the upper limit times 3. And there we have it. And what is this going to give me? Well, to the left, I can simplify 5 times 2 is 100. 100 by 2 is 50. 50 times 21 is 1050. And 20 times 3 is 60. So that sum should be 1110. See how quickly we can find the sum? Thanks to the properties and the formula that we have. Let's try another one. Let's say k goes from 1 to 16, and we're going to go of k squared plus 4. Again, this time you don't have to write this and do the arithmetic, use a calculator. We're going to first break it into two sums of k squared and sigma of 4. Right? It goes from 1 to 16 like that. Well, sigma of k squared, we had a formula for that. There is sigma of k squared, right? It's n plus 1, 2n plus 1 over 6. N here is 16, by the way, right? This is n in our formulas. So n, that would be 16. N plus 1 is 17. 2n plus 1, that's 2 times 16 plus 1. Divided by 6, plus the sum of a constant. You multiply upper limit times the constant. We did that here also in my previous example. Okay, and then we simplify the work and do the computation. I got 1560 for this one. Cool. Let's do one last one. This next example, suppose I'm going to start k5 now to 20 of k cubed. See, I'm not starting at 1. So what am I going to use? I'm going to use number 4. It says to find the sum from somewhere in the middle of the series. You go from 1 to n and you subtract from 1 up to the one before you want to start with. So I want to start. So this is what the sum would look like, by the way. 5 cubed, 6 cubed, and so on, plus 20 cubed, right? So what we're saying is this. Why don't I do sigma from 1 to 20 of k cubed, and then subtract from it? Because when I go from 1 to 20, am I not doing 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on, right? Isn't that what I'm doing? But then if you look at that, I only want from the from 5 cubed to 20 cubed. So these are all extra, aren't they? Therefore, I need to subtract them. That's why we are subtracting from 1 to 4, not to 5, but you go 1 before. 1 to 4 of k cubed from it. So we're going to count the whole series and knock out the first 4. That's what we're doing with our formulas. Okay. And having done that, let's see, the formula for k cubed is up here again, number 8. This is a formula for k cubed. It's n, and remember, n is the upper limit of the summation. So it's n plus 1 over 2. It looks exactly like number 6. The difference, you square it. Okay, the right side. So that's going to be n times n plus 1 divided by 2, and then don't forget you square it, minus from 1 to 4, that's going to be 4 times n plus 1 is 5 divided by 2, and then you square this one because that's what the formula calls for. Now 20 times 21 squared, 20 by 2 is 10, 10 times 21 is 210, 210 squared is 44,100. 4 times 5, 20 by 2, 10, 10 squared is 100, so I'm going to subtract 100 from it, and the answer is going to be 44,000. And there you have it. See how that works? And all that you wanted to know about sequences and series. Now, this is just general discussion about sequences, series. Okay, we have many well-known sequences as series. So our next 2 sections at least, we're going to take on 2 very specific sequences. We're going to look at arithmetic sequences and series, and we're going to look at geometric sequences and series. Okay, but for now we are done with this lecture and with this section. Again, thank you for watching, everyone, and hope to have you in another video. Goodbye.